goes, means one particle remain in the ground level, the next particle goes into the high level, the next level. So you got an excited state. This is one configuration, and we get this energy. For the other configuration, we got the same energy. So what does it mean? This means that the state is doubly degenerate. These are two states, N1 and N2, and we got the same energy for those states. And you earlier noted that when two or more states share the same energy, we say those states are degenerate. So I will call that these states are doubly degenerate, because the states are two while they share the same energy. And what about the wave functions? The wave functions will be sine 1, 2. So it will be equal to 2 over a sine n1 is 1, so pi x1 over a, and sine pi x2 over a. Sorry, this will become 2. 2 pi x2, because in 2 is 2 here. And 2 is 2 here. While sine 2, 1 is equal to 2 over a sine pi 2 pi x1 over a, and sine pi x2 over a. Are these two states different from each other?
Yes, sir.
It means these are two different states which are sharing the same energy. And that's why we call them, these two states are degenerate states. Doubly degenerate means they are two in number and they are sharing the same energy. If the states will be three and they share the same energy, we will say they are triply degenerate. Clear? Okay. Now we come to the case 2, and case 2 is of indistinguishable particles, or we say that they are identical particles. So these are identical particles. But in identical, we were having the situation of two different kind of particles. So I will first consider bosons. That these are bosons and fermions are both identical particles. But first I consider here identical bosons. In identical particles, the first I am considering bosons, and then I will consider fermions. Identical bosons. And now see that what will be the ground state. So the very first one, the ground state. Ground state means n1 is equal to 1 and 2 is equal to 1. So we will have first E1, 1. And this is equal to 1 square plus 1 square k, and this is equal to 2k. So like the distinguishable particles, the identical particles, bosons, are also sharing the same energy, which is equal to 2k. And what about the psi 1, 1? Now for identical particles, I now cannot write like this one. Psi R1, just their multiplications. Why? Because there are other possibilities, means these two are possible, these two are possible, but this configuration is also possible. Similarly, this configuration is also possible. Now when I come to the identical particles, I will have to write them like this, with plus and minus here. Clear? This will normalize it. This is the normalization constant. So I will have to come to that equation, and now I know that if the particles are bosons, so I will have to write plus sign here. And now let's start with this one, that what it will be. It will be sine 1, 1. So the wave function will come out to be A, and it will be first. It will be sine 1 into sine 1. Clear? So write 2 over A when both of these will multiply. Here we are having 2 multiplication, this one and this one. And over there we are having 1 multiplication. So 2 over A is sine pi x1 over A and sine pi x2 over A. Clear? This is part first. This is this part. Then plus 2 over A from here and 2 over A from the next. So we will have again 2 over A, then sine, and n is 1, and 1 is 1, and 2 is 1. So this will be pi x2 over A, because here we will write psi b first, and sine pi x1 over A, and it's closed. So what will happen? Sine pi x1, sine pi x2. I can write this pi x1 and pi x2, no problem with this. So it means that this is added with this. So 2 times A into this. Clear? So I got sine 1 is 2 times A, 2A sine pi x1 over A and pi sine pi x2 over A. This is our ground state wave function. Now look here. Our ground state wave function is 2 over A sine pi x1 over A pi x over A, x2 over A. What's the difference of this one and this one? Here you got 2A, here you got 2A is equal to 1 here. Clear? So this is the difference between this, and now we go to the first excited state. So okay, so sine 1 is equal to 2 times A this, and now the energy of this state, which is E11 ground state, and this is equal to 1 plus 1 K and equal to K. And 1 is 1 and 2 is 1. So we got for the distinguishable particle the ground state energy is 2K. For the identical bosons, we get the energy, ground state energy equal to 2K. And this is before. And now I will write for the first excited state. So the first excited state is first excited state. Now the first excited state, you know that this will be here, distinguishable particles. It was psi 1, 2 was one state and psi 2, 1 was another state. But what about the identical particles? Psi 1, 2 and psi 2, 1 are the same. So there is only one state because the particles are identical. So I will have that psi 1, 2 is equal to A times 2 over A sine, and 1 is 1, so pi x1 over A, and sine 2 pi x2 over A. Because in 1 is 1, in 2 is 2, so I have written 2 here, and plus 2 over A again, and sine, now in 2 here and x2 here, so 2 pi x2 over A, okay, 2 pi x2 over A in 1. So I will have 2 over A, 2 pi x2 over A, and then okay, x2. Now let me think of this. So you will have plus and plus here. So you will write psi b. And psi b it will be with 1 here, with 1 here. So it is pi x2 over A and sine 2 pi x1 over A. Clear? So you got the state like this, and 1 is 1 and 2 is 2. And what about the energy? The energy is 1, 2. So it is equal to 5K. What was the energy in terms of the first excited state of distinguishable particle? It was 5K. And this energy is also 5K. So the energies are the same. But in distinguishable particle, the excited state were doubly degenerate. While here we are having only one state. So it is a non-degenerate state. One state is here. And now we come to the case 3. And case 3 is the identical fermions. Case 3. Identical fermions. Now, this identical fermions I am solving, but this is your problem 5.4b. The A part you should solve. I am solving the B part, which is the identical fermions. And the very first is that I will have to write the state with energy 2K, right? This is the first excited state with energy 5K. So let's come to the state which is having energy means psi 1, 1. And it was having the energy 2K. Now I will write the same for this one, for the fermions. Look here. This will come out to be the same. and this will come out to be the same because it is psi 1 to 1. Clear? But the only difference for the fermions is that this sign is minus here. So when this sign becomes minus there, then this and this are cancelled. It is not adding up. Clear? So what will happen? That there is no E equals 2k state possible. Clear? There is no E equal to k because this is the state which is having the energy equals to 2k. Clear? This is having energy equal to 2k. Let me draw a line so that not to confuse this one with this. So it's from here, sine 1 1, and here plus sign was, so these two added up. For the fermions, here will be minus, and these two are cancelling. So we are having no state with energy 2k. Clear? And then what about the ground state then? Because no E equal to k state is here. Clear? E equal to k state is the ground state. For the distinguishable particles, S will S for the identical bosons. E equal to k is the ground state. And now the ground state for the identical fermions is sign equals to A times 2 over A will come in, and sine phi x1 over A and sine 2 pi x2 over A minus 2 over A sine 2 pi x1 over A and sine pi x2 over A. Now this state is different from the excited state of the identical bosons. States are different because here pi x1, pi x2, but here is plus and here is minus. And what will be the energy of this state? Means it is like psi 1, 2. Right? Psi 1, 2. Because 1 is here, 2 is here, then 2 and then 1. While the energy of this state, the energy of the 1, 2 state, or you can say, means in fermions I will not call this 1, 2, but just to make you understand. This is just sign. This is the ground state sign, and this is just the energy of the ground state. But in 1 is 1 and in 2 is 2. So I will have 1 plus 4k, and this is equal to 5k. You got the point?
Yes, sir.
Two fermions will be in two different states. You cannot combine them in one state. Either this one or this one. So the ground state of the fermions is having the energy equal to the excited state of the identical bosons, to the excited states of the distinguishable particles. You got it?
Yes.
And why? What's the reason? The reason is that two fermions don't like to sit on the same bench. As you are sitting 2 or 3 on one bench, fermions will always sit alone in a given state. Clear? And they differentiated from the identical bosons from the non-identical particles.
Yes.
Clear? So their ground state energy is equal to the first excited state of the distinguishable and indistinguishable bosons. Got it? So that's the differentiation between the two. In n infinite square well, you have different kinds of configurations for different kind of particles. Is in assignment, you can solve part A of this one, and you can additionally solve problem 5.3 and 5.4. You can solve this one in order to get more insight into the distribution or the configuration of different kinds of particles. Thank you.